Hi everyone, my name is Suxian. I am a graduate student at the Department of Astronomy at Ohio State University. In this short video, I'll walk you through my paper on the study of quasar selection in the dark energy survey supernova fields. The Dark Energy Survey, or DES, is an ongoing survey in the Southern Hemisphere that aims to study the nature of dark energy using various astrophysical probes, including supernovae. The fields that DES surveys for supernovae are known as the supernova fields, which are scanned more frequently and have deeper imaging. We focus particularly on two fields that overlap with SDSS-82, from which we derive our sample of truth quasars using the quasar catalog published by Peters et al. 2015. We divided our analysis into two magnitude limits, brighter than 19.8 and brighter than 22 magnitude in DES I-band. At the bright limit, Peters et al. 2015 have enough spectroscopic information to estimate the quasar completeness to be 94 to 95%. Although there are less spectroscopic confirmation of the quasars at the faint limit, the quasar catalog recovers around 98% of the spectroscopically confirmed quasars from the Bose catalogs up to I of 22 magnitude. Using our sample of truth quasars with more than 600 sources, as well as our sample of non-quasars consisting of objects that are not part of our quasar sample, we investigated the completeness and efficiency of various quasar selection methods. These are calculated relative to quasars and non-quasars in our sample that are point sources, pass off photometric cuts, and are detected in the required selection bands. I'll first go through the selection methods we investigated in this paper before summarizing the results at the end. First, we look at color selection of quasars. The first one is YSW1 minus W2 selection. The second one consists of DSGI and YSW1 bands. Another one consists of DSGI and BHSK band. The plots show where quasars and non-quasars fall in a three-color selection space, where we can see clear separations between the two groups. Next, we look into probabilistic selection of quasars using the XDQS algorithm, which calculates the probability of an object being a quasar given its fluxes. For our XDQSO implementation, we made use of the DS optical and the YSW1 and W2 bands, and set a cut at PQSO of greater than 0.5 for being selected as a quasar. The majority of non-quasars have low PQSO, while quasars mostly have PQSO greater than 0.5. Since quasars are known to exhibit around 10 to 20% variability over years timescale, we also investigated selecting quasars based on the chi-squared probability from a non-varying model. We used the GRI and Z band light curves from the DS01 data available at the time. This plot shows a fractional distribution of the quasars and non-quasars as a function of the reduced chi-squared, where non-quasars are well fit by a constant magnitude model and the quasars not so much. We chose a chi-squared probability threshold of 0.01, which corresponds to rejection of the non-varying model with 99% significance. One can also imagine combining these various selection methods. For this, we analyzed the performance of combining W1, W2 color selection, GIW1 color selection, and XDQSO selection with variability. The results from all the selection methods mentioned above are shown in this table. Besides the completeness and efficiency for each method, we also show the surface densities of the selected sources and quasars. While variability selection gives the highest surface density of quasars, there is also a substantial amount of contamination for non-quasars due to the selection efficiency. Since we only use data from the first year of DES, our variability selection based on chi-squared is mostly too simple. Selection based on more sophisticated variability models, such as the Denver network model, is deferred to the future when more DES data becomes available. Looking at the rest of the selection methods, the GIW1 color selection gives the highest quasar surface density among the individual selection methods, aside from variability. For combined selections, XDQSO plus variability is more efficient than W1, W2 plus variability and GIW1 plus variability, but it also returns lower quasar surface density. Last but not least, as a value added to the paper, we also released the OSS Quasar Catalog, which is a spectrophotometry catalog of around 1,200 spectroscopically confirmed quasars taken by the OSS survey. The paper is linked below, so please check it out for more details on the catalog and our quasar selection analysis. Thank you for watching.